Hello, how are you? I'm down here in the lower right-hand corner tonight. Change of pace, but tonight I'm going to discuss the circuits problem in another thinking out loud session, and add to that charting. Charting is something that I always do when I'm confronted with a circuit because I like to keep track of all the values, especially when it comes to the current as it divides and through the various branches, and then the voltage that drops at each of the resistors. Because sometimes in charting the circuit, just spewing out all the values, you end up with lots of answers that you can just simply list at a later time. Just, oh, I figured that out when I charted it. Yeah, the voltage drop across R3 is. So anyway, let's without further ado, let's get started. So here's a circuit, and in my mind, I'm imagining, thinking out loud, that once we close the circuit or turn the power source on, current begins to flow, and then it reaches what we call a steady state condition. That's when all the current sort of fill the pipeline, and each of the resistors are running at a particular voltage drop. You know, it heats up. There's some changes in characteristics of resistors because they're subject to heat, and as far as the values of the resistors. So here we go. I'm just going to start just sketching some stuff up here. Let's use my favorite color, red. And so we've got current leaving the battery, positive current. I'm going to call that big I. And then the I is going to pass through R1. So the value of I1 is the same as the I that leaves the battery. Now, when we get to this node or this branch or junction, the current's going to split. Some of it's going to go this way, and some of it's going to go that way. And it's based on the value of the resistance, in this case, the equivalent resistance each of these branches. And if you notice right away, you have 6 and 12, 12 and 6. So you have the same resistance each branch. So that current's going to divide in half at that node. Okay? So whatever current that leaves the battery, half the current is going to pass through R2 and R4, and the other half the current is going to pass through R3 and R5. All right. Let's read the question just for the sake of the question, because sometimes I don't read the question, I just start charting. But let's read it just for the sake of expediency. A circuit is created with an ideal battery and 5 resistors. With the values shown in the figure below, not above. An open circuit is shown that can connect points X and Y. So at a later time, we are going to throw that switch, and different things happen. A voltmeter V and an ammeter A1 are also shown in the figure. The switch is in the open position, okay, at the beginning. Calculate the current measured by the ammeter. Now, the ammeter is, I'm going to say, south of the negative terminal of the battery. But if you remember, when it comes to current or conservation of charge, the current that leaves the battery is equal to the current that returns the battery. So the current that leaves the battery is the same reading that you're going to get for A1. So in order to find the current leaves battery, you have to find the equivalent resistance. And then knowing the voltage at the source, divide that voltage by the equivalent resistance, and hence you'll get the current that leaves the battery. So I always have to, one of my impulses is to determine the equivalent resistance right off the bat. So let's do that. I'm going to back up that little dot there. So let's use yellow. The equivalent resistance of the circuit, we have a 2 ohm resistor that's in series with these 2 branches, which are definitely in parallel. Now, in each branch, there are two resistors in series. So in thinking about that, here's one-stop shopping calculation. I think you'll follow along. So Ohm's law, in terms of I is equal to the EMF at the source divided by the equivalent resistance. Okay, I call it big V over big R equals big I. All right, so we have 20 volts. Okay, and let's make a big old line divided by, here's the equivalent resistance. We've got 2 plus, now that's in series with the 6 and the 12 and the 12 and the 6 that are both, those sets of resistors are in series, but they're in parallel to one another. So this is how I'm going to go about it. Resistors in parallel is the inverse sum, okay? And now, in this case, we have 6 plus 12. So 1 over 6 plus 12, so those two together make up an equivalent resistance. It's parallel with the other 12 and 6, okay? And then we're going to add to that 1 over 12 plus 6, okay? See that? And then we flip it. Don't forget to flip that thing, okay? It's really important. So the equivalent resistance of the circuit is going to be, now I apologize, I didn't add those up on my calculator, but let's see if we can do it on our heads. All right, 1 over 18 plus 1 over 18 is 2 over 18. Flip it, 18 over 2, which is 9. 9 plus 2 is 11. So what you're going to get is 20 over an equivalent resistance of 11. I didn't change the color of my pen. Sorry about that. I will now. I'm a little informal tonight, folks, because with circuits, you got to be patient, and they are fun. And I'm going to stick with fun. All right, 20 divided by 11 is 1.82 amps. And I had said that the current, once it reaches that junction, is going to split evenly. So that gives us the current through R3 and R5, and the current through R2 and R4. So let's go ahead and fill in this chart. So filling in the chart, we have an equivalent resistance of 11 ohms. And we've determined that the current that leaves the battery, that's big I here, that's going to be 1.82. Okay, let's see if I can fit that all in that box. And as I said earlier, the current coming out of the battery is the same current through R1. Now, notice I'm spending a little bit more time filling in this chart. We've answered the question. The current that leaves the battery is equal to the current that returns the battery. So A1 is going to read 1.82 amps. Well, let's fill in a little bit more of this chart just for the heck of it. We've got, let's see, I said I of the battery is equal to I1. So that's also 1.82. Isn't this fun? Now, once the branching begins, I2 is going to be half because each branch has equal resistance, so it splits equally. And later you'll learn that current takes the path least resistant. So if each path is equal, then it's just going to divide up. So 1.82 divided by 2 is 0.909. So I guess we could round it up to 0.91. Okay, so 0.91 is going to be the current through R2, R3 0.91, I4 0.91, I5 0.91. So look at that. And as the saying goes, if you know two things, you can find the third, which means that we can I don't know if we quickly, but we can find the voltage drop across R1, R2, R3, R4, R5. Why voltage drop? Well, a resistor will dissipate electrical energy. So we consider the voltage across each of those resistors as a drop in electrical energy. So the resistor is dissipating energy in the form of heat. So that's a drop in electric potential. The battery is considered an electric potential, like a ball starting at 2 meters above the ground. But then as the ball falls toward the ground, it's losing gravitation potential. So in this case, this current, I'm going to call it current, but the voltage is dropping in electric potential. Kind of like that. Not really. But if you apply Kirchhoff's the loop rule, that's essentially the principle behind Kirchhoff's loop rule. It's just adding up all the potentials, and the net electric potential is equal to 0. I don't think we're going to apply Kirchhoff's loop rule today, or tonight, for that matter, because I don't know what time it is. But if you look at my clock, AM or PM, I'm not going to tell you. I'll let you guess. So let's fill in these voltages because we might be able to refer back to them and answer questions quickly. I know that part 2 of A wants to know the voltage drop across R3. So in doing so, finishing up the chart, that's what we get. So be a little patient here at first because I might have to pull out my calculator. All right. So the voltage across the voltage drop across R3. So if you know I3 and R3, you can find V3. So that'll be the voltage across R3. So we've got, let's see, I'll just write it out here. Let me change my pen to yellow. And so let's call it as V3. So that's that voltage there. And that's going to be equal to R3 times I3. So I'll use a little I, because some of that big I splits up into little i's. All right. So if you multiply 0.91 times 12 volts, or excuse me, 12 ohms, you'll get 10.91 volts. So that's your voltage drop. And I want you to remember that value at a later time. Those are just using a really easy equation. Ohm's law. What the heck? Calculus basic physics course. No calculus here. Just regular circuit stuff. Okay. Change my pen to red, and I'm just going to fill in the chart. That's the V drop at the 2 ohm resistor. So we'll call that V1. So that's, or no, excuse me, I take that back. That's V3. So right here. So that'll go in there as a 10.91. Now, folks, didn't I say that the current is the same through each of those resistors in both sides? So take a guess as to what that same voltage drop appears somewhere else. What do you say? Yep, you're right. 10.91 also is the drop across R4. So that's V4. So again, 10.91. And what's the voltage drop across the 6? Well, 1.82 times 6. Okay, so let me calculate that real quickly with my handy HP calculator. Okay, it says it was manufactured in 1986. Still works for me to this day. So I'm going to multiply 6 times that 0.91. Okay, and I get a voltage drop of 5.6. Let me take that back. I want to make sure I got that right. So I've got 6 times 0.91. Yes. Okay. I had another value in my mind, but yeah. So let's see. We've got a voltage drop across R2 and also R5. So we have 5.46 or 5.5 and a 5.46. Isn't this fun? Charting is fun. Now, V1, that's the voltage drop across R1. So just put a little meter there. So there's a voltage drop there. And that's going to be the total current that leaves the battery times 2. So let's stick it in there. I don't know if we'll need this value, but it's good to just have the impulse and the common knowledge to know that you can get any of these values at any time. Again, if you know 2 things, you can find the third. All right, so 1.82 total current that leaves the battery times 2, and you get 3.64. Okay, so you have a 3.64 drop. 3.64. Now, this is, I'm going to go on to say that. Check this out. You start out with 20 volts. You drop by the amount 3.64. Okay, if I take 20 minus, if I take 20 minus 3.64, I get 16.36. Okay, that means that I've got 16.36 volts left to power the other 4 resistors. And look how the voltage parts out or divides. Notice that the R2 and the R4, the sum of which is, you guessed it, 16.34, 10.91 plus 5.46. Pretty darn close, PDC. All right, if you didn't follow that, maybe I'll mention it at a later time. Hey, let's get off this page and start answering the rest of the problem. It might go a lot quicker than maybe I think, but let's see what happens. I hope this has been helpful. Okay, calculate the potential difference measured by the voltmeter. Done. We did it. We did it. We calculated, and that was V3. And if I remember, I'm going to take a quick peek back at my chart. Okay, 10.91, right? All right, 10.91 volts. That's a drop in electrical potential energy at that 12 ohm resistor. It should make sense. The larger the resistance, the greater the dissipation of the electrical energy. All right, let's go on to the next question. Okay. All right. Okay. The switch is now moved to the closed position. Okay. Now notice here I have a chart that says when the switch is closed. So I'm going to chart a little bit. I don't know if I'm going to chart it all, but we'll see how far we get, because I didn't want to over-explain. I know that we have a limited amount of time. However, allowing me to explain and give you the practice, sort of positive growth mindset, is that what they say? The approach to this problem, embrace it with love and care. I think the problem will return to you an answer that reflects the amount of energy and time you put into it. Okay, so as I say, take what nature gives you. In this case, take what the circuit gives you. Okay, gives you an opportunity to flex your electrical engineering hat. All right, let's keep going. Okay, we're gonna close this switch. What happens? Well, I'm gonna diagram something to give you a little sense of what goes on. Here's what I'm drawing here is that 6 ohm resistor R2. Okay, and then alongside it is that 12 ohm resistor R3. Now, notice that when that switch is closed, you might as well just squeeze that point over there and just join them up. And I'm going to show that in this diagram. So instead of like having a long wire between them, you can actually replace it with, connecting right there, create a node, a junction. And then I'm going to show the 12 ohm resistor and the 6 ohm resistor. So here's R4, that 12 ohm resistor, and then here's R5, that 6 ohm resistor. That's the same diagram, folks. That's the same diagram. It might as well be the same diagram. So look what we did. What we did was we created what was a parallel branch. One parallel branch with 2 resistors in series. We created 2 parallel branches. There's one now, and there's another one. Okay, isn't that cool? All right, so that's essentially what closing the switch does. And this diagram is going to come in handy in helping explain why the current does what it does when it rushes to the junction and then splits again. Okay, all right, so hang with me. All right, since we have the switch closed, we have a new equivalent resistance because we've got now 2 parallel branches. Okay, I'm gonna get rid of my dot stuff. Here we go, back to solid. And so the new equivalent resistance is, okay, I'm not gonna do the big equation all at once, but I'm gonna go be really patient. So here's the new equivalent resistance. Get a little space here. Okay, just like that. All right. We've got 2 ohm is still in series. Okay, it's still in series with these 2 that are in parallel. So we're just going to add this parallel branch to this parallel branch. So this parallel branch, the above one, is in series with the parallel branch below. So we've got 2 sets of parallel resistors. So parallel resistors is added like this. 1 over 6 plus 1 over 12, and then flip it. And you got another one in series. So it's the same thing. 1 over 12 plus 1 over 6. And don't forget to flip it. Take the inverse. All right. They're really nice too. You can do this in your head. You don't have to pull out your calculator. So let's do this. Okay. We know what 2 plus is. 1 over 6 plus 1 over 12. Common denominator, 12. That would be 3 over 12. 12 over 3. Again, don't forget to flip it. 12 divided by 3 is 4. And same deal, 4. 2 plus 4 plus 4. 10. Oh, that is so cool. So we get an equivalent resistance of 10 total in the circuit. So I'm going to put it right here. I'm going to put 10. Before, what was the equivalent resistance before? That was 11, wasn't it? Not a pretty number, you know. But, you know, we can do it, 10. And check this out. What's 20 divided by 10? Remember what I said? If you know two things, you can find the third. So big V divided by big R, that's Ohm's law, is equal to big I. So 20 divided by 10 is 2. Whoops, got to change color. Sorry about that. All right, can't see yellow on white. All right, here's red. All right, so 2. Now, let's go back to our junction. Remember how the current split in 2? Well, it doesn't split in 2 in this case. Yes, some of the current will go this way and some of the current will go this way. But since we're considering this a separate parallel section, which is in series with the lower one, the current's going to take the path of least resistance. We do have a least resistance path here, and that is the 6 ohms. Now, we could use Ohm's law, you know, and figure out what the voltage drop across 6 ohm is, and knowing 6, you can find the current. But I'm going to propose this method. In my mind, will take this current that reaches that junction here. Let's call it junction A, and it's going to split proportionally. Watch how I set a proportion. Okay, back to my yellow line. So I might need a little room here, but let's see. I'm going to do some erasing. Not too much erasing, but just have a little room right about here. Okay. All right. We have a 2-to-1 ratio. 12 is twice 6. But the current takes the path least resistance. So when I set up this ratio in terms of how much current goes to the 6 and the 12, more of the current will go through the 6 and the 12 based on how I set the proportion up. So this is how I do it. Since I've got currents splitting at junction A, this is how I set up my ratio. Okay, I got 2 numbers. I'm setting up 2 numbers here, something divided by something. This is how you do it. You've got 2 to 1. So you go 2 plus 1, put that in the denominator for both. And that gives you a 3. So some of the current is going to go through one of the resistors, and more of the current is going to go through the other. But watch what I do. 1 over 3 and 2 over 3. There's that 2-to-1 ratio. So this number, 2/3 and 1/3, will be the proportion of the 2 amps that flows through that branch. So so here's the question. What is 2/3 of 2 and 1/3 of 2? Okay, so this is the current that's going to split at junction A. So 4/3, last time I checked, was 1.67. No, check it. No, that's not last time I checked. 4/3. Okay. 4/3. I gotta look at my notes here. See, I got notes. Okay. Engineering computational paper. I hope you keep track of your thoughts. So I've got 2/3 of 4/3. Pardon me, 2/3 and 4/3. When I say 4/3, so 4/3 is 1.33. Okay, last time I checked. Okay, sorry about that. I'm kind of messing up here. Gotta go backwards. All right, so let's go back to the action. So this is going to be 1.33 amps flowing through the least resistant path, and the most resistant path, that's going to get the balance of 2. So that's going to be 0.67 amps. All right. Now, excuse me that I'm not writing out the units, but current is measured in amps. So both these, that's what that means, amps. All right. Okay. Sorry about the being a little sloppy here. So I'm going to fill my chart in with the current that flows through the 6 ohm resistor, and then subsequently the other portion of 2 is going to flow through the 12 ohm resistor. I know this this video is taking a little longer than 10, 11 minutes, but it's all worth it. I promise you. Working through this problem and owning it will serve you well in future problems. Promise. All right. So let's see. R2. So that's going to be I2. Okay, so I2 is going to be 1.33. Okay. And R3 is going to be the balance of 2. So 2 minus 1.33 is 0.67. Okay, here we go, 67. Now, here's the fun part. All right, I'm going to go to my highlighter. I think let's go with orange with my highlighter. So this is what happens here. Here's my highlighter. I'm going to be able to do that kind of thing. All right. So here's what goes on. The 1.33 current is going to flow, reach the junction, and then it's going to jump the other side. Not jump, but that's the path it's going to take. The larger current is going to take the path of least resistance. So that's the direction at which it's taking. Let me pen that on this diagram here. So essentially, the current that goes to the 6 ohm resistor will serpentine like that. Here, I'm going to erase that just to kind of clear up that. Okay, make this point again. So once the current, that 2 amps reaches that junction, folks, this is how the current's going to do. It's going to go to this. All right. Now, understand that switch is closed. The current that goes to the R3, the 12 ohm resistor, is going to likewise go like that. Okay. So that's the path. So the current entering the junction is equal to the current that exits the junction. That's that junction right there. And then it splits again, proportionally, taking the path of least resistance. So that's how it's doing that thing. Okay. Again, current that goes to R3 crosses over that junction and it continues through R4. Okay, the smaller the current. Okay. All right. So that's my explanation as to how that current kind of does what it does. Taking that little turn there at the junction. And since I said junction as much, let's call it junction B. Okay, let's call it junction B for the sake of discussion. So here's junction A. Okay, junction A, it splits, the 2 amps splits, 0.67, 1.33. And then when we get to junction B, that 1.3 will move on over to the right, pass through R5. Okay, and then the 0.67 that branches that away. Okay, that 0.67 is going to then pass through the 12 ohm resistor, reach junction B, and continue to pass to the left through R12. That's what's going on. Okay, all right. Now the current through R3 and R4 are the same. Okay, so R3 and R4 are the same, so 0.67. And the current through R2 and R5 is the same. Okay, I'm just going to chart that. I1, I didn't specify I1, but the current coming out of the battery is the same current that goes to that 2 ohm resistor. Now, do we need to fill in any of these potential drops? I don't know. I did it earlier, but let's see if it's asked once again, if there's a potential drop anywhere. What's the new potential drop would be? It could be. We'll see. All right, let's move right along. Hopefully this has been helpful. Next page. All right, a student wants to determine if there is a current in the closed switch. The switch is now replaced with an ammeter A2 between points X and Y. Ammeter acts as a closed switch and can measure the current. Calculate the current measured by ammeter 2. Well, I think I've said in the previous page, I'm going to go back to the previous page. I think I said a lot of stuff that might suggest as much. But let's look at it further. I'm going to go through that. I'm not going to go through the explanation again, but I'm going to do this just symbolic path again. Okay, so here is the path of the 1.33 amps. Okay, and then here's that junction B. Here's that junction B that I said. So 1.33 goes on over to the right-hand side through R5, and that's the 1.33. Okay, same deal. The current through the 6 on the left-hand side above junction B is the same as the current through the right-hand side below junction B. And likewise, the current that flows through R3 passes through that junction B, then flows through R4. Okay, so that's that 0.67. A lot of people like to see a 0 there, 0.67. Okay, let me just clean that up a little bit for the sake of discussion. So 0.67 amps is going to flow through R3 and then reach junction B and move through the 12 ohm resistor. Remember, current takes the path resistance. Okay, so in one junction, out the other, and back through, another set of resistors, 12 and 6. Current taking the path resistance, more of it. That's what's there at the junction. Okay, so that's also a 0.67. All right. Now, I'm going to point your attention to, I'm going to go to an arrow thing, kind of give you the direction, and I think pink, bright pink will show up. It's just nice. So here's this arrow represents the 1.33 amps. Oh, it didn't make an arrow for me. Apologize. Let me put a head on that one. Okay. This arrow represents the 1.33 amps. Okay. All right. 1.33 amps. That's the direction at which the current is kind of making that jump over to the right-hand side. The current that flows opposite, goes from, so when I say, I should probably specify that. That's the X side and that's the Y side. So the current's going to go from X to Y once it reaches junction B. Now, let's look at the direction at which the 0.67 flows. I'm going to switch that to green. Okay. All right, watch this. Okay, there it goes. And I'm going to show the arrow a little smaller. Okay, so the relative magnitude of those two arrows, kind of like a vector, but it's just the direction at which things are headed. That's at 0.67. Okay, that represents the 0.67 amps. And if you take the sum of those, the ammeter reading, folks, is going to be the net current that flows between X and Y. So if you've got 1.33 going that way, and you've got 0.67 going that way, the net ammeter reading is going to be, you guessed it, 0.67 amps. So the current from X to Y, the ammeter reading, okay, A2, okay, let me check my pen. The A2 reading in this scenario, having described how the current does what it does, takes the path that it does, going into junction B and then out again through the 6 and 12, we have 0.67 amps. Okay, and I'm using the direction of positive, negative. So think of it as the, kind of doing this kind of thing, back and forth. And guess who wins? Okay, it's like taking three 1.5 volt batteries, not quite, and add them together, and you get 4.5. But if you take one of the batteries and reverse the polarity, you're going to subtract 1.5. So your three batteries equals 1.5. And the poles, the bias, just because you switched one, will be in the same direction. So that 1.33 is greater than 0.67 in the other direction. So therefore, the net current and direction will be XY. Okay? In the direction XY. Indicate the direction of current, if any, through, oh, just did it. Okay? It's to the right. Okay? And do they ask us to justify it? Well, this diagram does a pretty good job of justifying it. And if need be. Okay? Let's go on to the last page. I think it's the last page. Ammeter A is replaced with switch S and capacitor C equals 12 microfarads. All right, I get an alarm bell always goes off when I get microfarads. So remember that 12 microfarads, okay, that's a micro, is equal to 12 times 10 to the negative 6 farads. Okay, so that's what a micro is. Remember that. Okay, switch S is closed. So we're going to close the switch. All right, this is what I know about capacitors. And I think you know as much as well, because I did a little demonstration, and I showed you on a voltage versus time graph the charging of a capacitor as a function of time, or the voltage across the capacitor as a function of time, and you saw it go like this. Okay, so it takes no time at all to charge within 63% of the max voltage. Okay, a couple of tenths of a second. I think in the case of that 1 farad capacitor, I don't know if I had it hooked up to a resistor, but that was the demonstration a little while ago. And so there's a steady state thing going on. Usually steady state current, when a circuit reaches steady state, but there's no capacitor in it, it happens pronto. But when you have a capacitor in that circuit, you ease the steady state condition. So it takes a little longer for everything to reach steady state, provided that you leave the capacitor in there and you don't switch it and discharge it. So let's take it from that point of view. Oh, and I guess it would be helpful to read. But having said that, calculate the charge stored on the positive plate of the capacitor a long time after the switch is closed. Okay. Let's say this, okay, before we continue with the discussion. Okay, we can throw the switch and we let that capacitor charge up to its max value. Owing to the potential in that branch of the circuit. So when the charge carriers accumulate, it looks like the charge carrier is going to accumulate on this side, and then the negative charge carriers on that side. No more current's going to flow, okay? No more current's going to flow after a long time. So guess what? That capacitor between X, Y is, you might as well just treat that circuit just like this one, okay? Just like the original circuit. So guess what? See these values in our this chart? And I'm going to bring the chart over. Okay, a little magic. Watch this magic. Now, hopefully I can do this. I'm going to bring this whole chart over because I don't want to waste this work. Let's see if I can get all this guy. Uh-oh. I don't think I'm going to get it all over, but I didn't quite. I wasn't successful. That was a fail. But if we have to go back and reference it, I'll just click over. I'll just go over a couple of slides. Okay. Calculate charge stored on the positive plate capacitor. Okay. This is what I know in terms of the charge on the capacitor, the relationship capacitance is equal to, oh no, excuse me. Okay, I'm pulling this out of my memory bank. Okay, if I look on an equation sheet, the charge that accumulates on a capacitor is equal to the capacitance times the voltage that appears across it. Okay, so if you take a voltmeter reading, oh, wrong color pen. If you take a voltmeter reading across XY, that will be the voltage, and that's going to be our task. We have to figure out what that voltage is, and I'll walk you through that process. Okay, I just need to switch colors here. So if I go back to if I figure out what the voltage is, across this little segment, then that'll give me this value, in which, of course, I can multiply by C, and that gives me the charge stored in the capacitor. All right, so how do you do that? Well, have you ever played the voltage drop game? Okay, the voltage drop game is if you were to take a multimeter, okay, this is the voltage drop game, right? And you measure the voltage across the power supply. What do you get? Yeah, 20 volts. Now, if you take this lead, okay, if you take that lead and move it, if you move this lead over across, if you kind of bring that lead and bring it there, you're going to measure 20 minus V1. Okay, see where I'm going with this? And it's called the voltage drop game. So I'm going to take my voltmeter and go from here to over here. That's 20 minus whatever the voltage drop across R1 is. And I charted it, so I know it. I don't remember it off the bat, but we'll go back there. Then you go here. And if you put that voltage here, you're going to go 20 minus V1 minus V2. And that gives you the voltage in this vicinity. Okay. Now, if we backtrack, watch this. Okay. So we've got. I'm gonna sketch this out just so you see it. The voltage drop. Okay. So I go from 20, and I'm going to subtract V1. Okay, so I'm dropping by V1, and then I'm going to drop by V2. Okay, so I'm negative V2. Now let's take this lead here from the voltage. I see. Ooh, I can grab that. And if I do this, okay, I'm not changing the voltage at all. I'm staying on a single wire that has no resistance. I'm not dropping. And watch what happens. What if I place it here? The other end of the lead of the multimeter. Then I'm going to drop by another, that's R5. Okay, that would be V5. So this will be the voltage that's read across XY. Isn't that cool? All right. Now, I'm going to go back to that chart, and let's see if we can memorize those voltages. Okay, the original chart. Oh, man. I might have to write them down. What do you think? Okay, we'll just flip back and forth. So 20 minus 3.64. Oh, I think we can do it. We just base it off this chart. So I'm gonna grab my calculator, my HP, okay, reverse Polish, and I'm gonna get that cursor out of my face. So okay, this is gonna give me the voltage across the capacitor after a long time. All right. So 20 minus the 3.64. And we already calculated this number. I know. All right. Then we're going to then take that lead and place it on the other side of, I wish I could point to it. Oh, okay, I'll get my pen back. Okay, now we're going to take the lead of that voltmeter and place it here. Okay, we're going to drop by another voltage across R2. So I'm going to track V2, so 5.46. Okay, so I'm going to subtract that. I'm down to 10.9. Now, the other lead, the other lead that was over here to start with, measuring my voltage, okay, I am now going to move that in this position and cross over R5. That's going to include the drop R5. So I'm going to subtract another 5.46. 5.46, okay. Wow, okay. So I found the cumulative drop playing the voltage game. That's called the voltage game. It's fun. Love electricity and magnetism. I love this stuff. Okay, so after you subtract that, we get, okay, I'm not really paying attention to my color of pen, but let me make an adjustment there. I'm having fun, guys. I'm gonna post this one because I'm thinking out loud. And when you think out loud, it's okay to have wild thoughts and make mistakes. Remember, what did I say? If you're not struggling, struggle early to succeed sooner. And I guess what I start out with. And remember, that's where breakthrough happens. You struggle a little bit, and then comes the breakthrough. All right, enough said. Going back to my yellow pen, and 20 minus all that stuff is going to give me a whopping 5.44 volts. So that's the potential across the capacitor. So if you multiply 12 times 10 to the negative 6 farads times 5.44 volts, you're going to get the charge on the capacitor accumulating to, I know I'm cheating, 6.48 times 10 to the, bingo, you guessed it, minus 5 coulombs. All right, so there's the charge that accumulates in the capacitor. I know I spent some time explaining it, but these thoughts will become tested in your mind. Again, I'm a big fan of charting. Oh, notice that I cut myself. That's a Band-Aid. And I like to think about how that current does what it does when it leaves the battery and how it branches. And once it branches, the voltage drops. So this will all become second nature. I know it. Practice makes perfect. Okay. Oh, check this out. Which point X or Y is at the higher electric potential? Okay. I'm going to say this is easier said than done in explaining, but here's how I'm going to explain it. Over here, I'm just going to use this concept here. X is the positive plate, okay, of that capacitor. When I say, X and Y, notice that we have positive accumulating on the left-hand plate of the capacitor, and subsequently we have negative. Okay, conventional charge, or excuse me, conventional charge flow, or conventional current is positive to negative, as if we have a positive charge that's flowing, okay, from X to Y, and by definition of electric potential, this plate is at the high side of the potential difference. This is the high side. Should stand to show. When we first learned electric potential and electric potential difference, and it was first referenced in terms of a positive charge and the direction at which that positive charge would move in the electric field. Okay, that's an electric field. That's what sets up in a capacitor, and this is the low side. So X is at the higher potential. All right, that's all I have to say, folks, tonight, or today for that matter, because you can't tell what time of day it is. It could be early in the morning, or it could be late at night. But I do this. I guess they say I shouldn't say this, but I will work hard so you can work yours, if you know what I mean. All right, have a good evening, or day for that matter.